Hi everyone, welcome to Mathly. In today's episode, we are diving into the fascinating world of neural networks, one of the core concepts behind artificial intelligence and deep learning. From recognizing faces in photos to powering self-driving cars and recommending the next video on YouTube, neural networks are everywhere. But how do they actually work? Just like our brains have neurons that communicate and learn from experience, neural networks mimic this behavior in a simplified and mathematical way. And the best part, you don't need to be a coding expert to try it out. In this video, I will walk you through how neural networks work and show you how to build one step by step using orange data mining. Let's get started. Imagine trying to recognize your friend in a photo. Your brain processes patterns in shapes, colors, and positions to make a decision. Neural networks do something similar as they process data through layers of virtual neurons to find patterns and make predictions. At its core, a neural network is a system of interconnected nodes inspired by the structure of the human brain. These nodes are organized into the following layers: an input layer, one or more hidden layers, and an output layer. Each connection between neurons has a weight which adjusts as the network learns from data. Neural networks are particularly good at handling complex tasks like image classification, voice recognition, and even playing games. Now that we know what they are, let's break down how they actually work. Neural networks are powerful models that learn from data by mimicking how the human brain processes information. Let's break down how they work step by step. Step 1. Data flows through layers of neurons. Think of a neural network as a layered system where information flows from one end to the other. It starts with the input layer, which receives raw data like pixels from an image or numbers from a spreadsheet. Then comes one or more hidden layers where most of the processing takes place. Each neuron in these layers takes input, multiplies it by a weight, adds a bias, and then passes the result through an activation function that determines whether the neuron should fire or not. Finally, the output layer produces the result like a predicted label or a numeric value. The connections between neurons have weights, and these weights determine the influence one neuron has over another. Initially, these weights are random, but they get adjusted as the network learns. Step 2. Learning through training, also known as backpropagation. Neural networks learn using a process called training, often involving thousands of examples. Here's how that happens. The network makes a prediction using the current weights. It then compares the prediction to the correct answer using a loss function, a measure of error. Using backpropagation, the error is sent backwards through the network, adjusting the weights slightly to reduce the error. This process is repeated over and over, called epochs, until the network becomes accurate. This is how a neural network improves by gradually reducing its mistakes through many training cycles. Step 3. Making predictions and generalizing. Once trained, the neural network can make predictions on new, unseen data. This is called generalization. For example, a network trained on thousands of cat and dog images can accurately identify a new image it's never seen before. Or a neural network trained on historical sales data can predict future demand. The more diverse and well-labeled the training data, the better the network will perform on real-world tasks. Now, let's take a look at how we have set up our workflow in Orange Data Mining to perform a neural network on the heart failure dataset from Kaggle. To start, I have imported a heart failure dataset which contains clinical and personal information of patients. This dataset is often used to predict the presence or absence of heart disease using various medical attributes. Next, we have connected the data table widget to inspect the dataset. It contains 918 patient records with various medical attributes. The target column is heart disease, which indicates whether a patient is diagnosed with heart disease. Now, let's take a look at the neural network widget we have used for classification. In this setup, we have configured the model with 100 neurons in the hidden layer, which allows it to learn complex patterns in the data. The activation function is set to ReLU, or rectified linear unit, a popular choice that helps the network converge faster by introducing nonlinearity. For optimization, we are using the Adams solver, which is an adaptive learning algorithm. After training the neural network model, we have connected it to the test and score widget to evaluate its performance. Here we see several important metrics. Area under the curve is 0.914, which tells us how well the model can distinguish between patients with and without heart disease. A value closer to 1 means excellent discrimination. Classification accuracy is 0.854, meaning the model correctly predicts heart disease in about 85% of the cases. Precision, recall, and F1 scores are all 0.854, showing a good balance between correctly identified positive cases and missed or misclassified ones. Matthew's correlation coefficient is 0.704, a robust metric that accounts for true and false positives and negatives. This indicates strong overall performance even when class distributions are imbalanced. Next, we look at the confusion matrix to see how well the model performed in classifying the two classes, 0 for no heart disease and 1 for heart disease. The model correctly predicted 341 out of 410 cases with no heart disease and 443 out of 508 cases with heart disease. There were 69 false positives where the model incorrectly predicted heart disease and 65 false negatives where it missed actual cases of heart disease. Overall, this confirms the model is doing a strong job, especially considering how close correct predictions are to the total numbers in each class. Then we use the ROC analysis widget to evaluate the model's performance in terms of classification thresholds. The ROC curve shows the trade-off between the true positive rate sensitivity and the false positive rate 1 minus specificity. A model with perfect performance would reach the top left corner of the graph. Here, our neural network model performs quite well as the curve rises sharply towards the top left. The area under the curve is approximately 0.914, which indicates a high ability of the model to distinguish between two classes, whether someone has heart disease or not. Finally, I have imported another test file that contains 10 rows of new unseen data. As you can see in the data table widget, this data will be used to test how well our trained neural network model performs on data it hasn't seen before. Next, I have added the predictions widget to evaluate how the model performs with the testing data. By looking at the results, we can see how well the model performs on unseen data. All the rows are accurately predicted. You can clearly see that from the left side neural network column and can see the error rate of the prediction in the next column. And the grayed out heart disease column shows the actual value of the particular row. With this, the workflow is complete, showing how orange data mining helps build and test neural network models easily. Now, let's explore some real-world applications of neural networks. Image recognition and self-driving cars. Neural networks are at the heart of computer vision systems, whether it's recognizing objects in photos or detecting pedestrians in self-driving cars. Convolutional neural networks, or CNNs, help machines understand visual data with human-like accuracy. Healthcare and medical imaging. In medical diagnosis, neural networks analyze X-rays, MRIs, and CT scans to detect abnormalities like tumors or fractures. They help doctors make faster and more accurate diagnoses, especially in areas with limited access to specialists. Natural language processing and chatbots. Neural networks power virtual assistants like ChatGPT, Siri, and Alexa. They understand and generate human language using models trained on massive amounts of text, enabling accurate language translation, sentiment analysis, and intelligent conversations. Fraud detection in banking. Banks use neural networks to spot unusual transaction patterns that may signal fraud. These models learn from past behavior and flag suspicious activity in real time, helping protect customers and financial institutions. Personalized recommendations. From Netflix to Amazon, neural networks analyze your preferences and behavior to recommend movies, products, or music you're likely to enjoy. These models adapt as you interact more, making your experience smarter and more personalized over time. And that is a quick dive into neural networks and how they work using real world examples to illustrate their power in fields like image recognition, healthcare, natural language processing, and more. Neural networks have revolutionized the way we approach complex tasks, from self driving cars to personalized recommendations. By learning patterns in data, they make predictions with human like accuracy, and they are only getting smarter over time. If you found this video helpful, don't forget to like, share, and subscribe to Mathly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.